Hi, everyone. My name is Ben. I'm very glad to be here. Today, I'm going to talk about how to, some of our analysis and observation in optimizing GPU utilization for working workloads like training in Kubernetes environment. So my name is Ben, as mentioned. I'm the founding engineer and right now the VP of technology from Alluxio. Alluxio is a startup company in Silicon Valley, and we started from UC Berkeley AMP lab, working on big data, like acceleration for big data and query engines or ETL engines. But starting from like a few years ago, we shifted the focus to AI workloads. Here's my email, my LinkedIn. If you are interested, you can follow me. Priorly, I worked in Google, and I got my PhD from computer science in CMU. Okay. So to start this talk, I want to share some of my observations in my past, I would say, 12 months by engaging with different people in the data and AI infra ecosystem. First of all, I think like no one will be surprised. We're seeing a monumental investment in building this AI compute fabric. Tons of money, talent, and priority is putting into different enterprise. These days you hear always AI first for almost all the technology-driven companies. Okay, so in this process, we're seeing the enterprises, they are racing to build their own AI factories for to maximize the token velocity and efficiency. And you can see also, I'm actually paraphrasing the word AI factory. Jensen Huang was using this in the GTC 25, but basically you can imagine these days the factory is producing tokens or predictions instead of goods, but it takes data in, takes queries in. So in building this kind of factory, so a lot of companies, they're doing this by repurpose their data centers, but also there are a growing number of hosted service providing GPUs or similar platforms. So that's basically, I'm saying there's a lot of investment, a lot of efforts to build up this AI compute fabric. Okay, since I mentioned data, on the other side, you may or may not notice that actually there's at least from my perspective, I see a very, very, very clear trend that people are moving to cloud storage to build their data lakes. Even the most conservative sectors, I'm talking about banking, I'm talking about this type of very conservative sections, starting from maybe last year, it's already happening that they made a decision that, yeah, in the future, the data lakes are no longer in the on-premise data warehouse, but they're moving to public cloud, using the object storage as their way, as a backhand to build their data lakes. Well, one of the reasons is the cloud object store, like S3 or GCS, they provide a very scalable and very cost-effective storage capacity for petabytes or many petabytes. And also these days, you can see the data formats for data lakes, file formats, table formats, are also getting more standardized. Like for example, Parquet and Iceberg, they are dominating these days. Okay. So on one hand, a lot of infrastructure are building for AI, for token generation. On the other side, a lot of data, they're moving to the cloud-based data lakes as their final destination. Okay, so is there a gap or is there any disconnection here? I call this the data last mile problem. Essentially, once you have all these factories, they are producing tokens and they are relying on the data to build better models or to refine models. But on the other side, the data, enterprise scale data, lives in the cloud or in some cloud storage solutions for data lakes. So now, how to make your data in the lake, in the cloud, at the scale of enterprise or sometimes like many petabytes, available and efficiently accessible to fuel the token engines for AI compute fabrics. So that is what I call the data last mile problem, okay? Another dimension for this is really, in different stage for these AI life cycles, you may need data in a very different way or relatively different requirements. For example, for data pre-processing, from time to time, and people are asking for very highly concurrent and also high speed, both read and write. For compute engines like Spark, they're doing a lot of labeling and data cleaning. On the model training phase, people are building their models. Like from the previous panel, like definitely I heard opinions like, yeah, people are not building their models on one hand because OpenAI and Facebook or Microsoft, Google, they are building their models and they are put a lot of resource there. On the other side, I also noticed, like at least in my engagement, in very domain-specific industries, like robotics, they're building their models from scratch a lot. Because these models for robotics arms, like for example, it is their business advantage, like if you sell the arms, robotics arms. So it depends on really the sectors. I also, like in some other healthcare or some other sectors, people are still building these training models. So support high-speed data sets reading at petabytes or billions of objects at scale is perhaps something a requirement for this stage. And meanwhile, like for example, making sure you can asynchronously checkpointing the models from GPUs to somewhere in the data lake fast is also part of the requirement in here. We also have I put this as a model distribution, like I don't know if you are aware of, like when you are using, for example, if you're using agentic programming or like a web programming, like Cursor. In the meanwhile, you have a lot of actual inferencing happens, and you have to leveraging on these inferencing service providers to use the latest model weights fine-tuned for you. Okay, so this requires these model providers or these service providers, they distribute these models efficiently and in a very cost-effective way to different edge of the internet globally. Actually, I'm talking about, like, for example, this type of inferencing providers, inferencing service providers, they need to move the data. In order for the inferencing to happen, they need to move the model weights from centralized model repos, for example, on GCS or on AWS, to different edge inferencing clusters. So that also needs to be very highly concurrent and high speed, and typically for huge models. If you take a look, like latest model weights for the state-of-the-art open source models, they're already reaching multiple tens of models, and for the closed source models, it's even much bigger, like 10 times bigger than that. On the inferencing side, it's also getting very interesting. As you may know, inferencing is getting more and more attention compared to, especially starting from this year. And a lot of sub-millisecond require fast retrieval for certain data is crucial to enable agentic workloads. For example, you need to check the memory, the short-term memory and long-term memory before you do any agentic inference to provide a better and more accurate result. And during the inference, there's also needs to have a very fast read and write to support KV cache. So all this, adding them together, you can see there's a lot in different stages. There's a lot of different requirement for data and also for I/O. Okay. So this is a very common architecture we have seen in the field. People are using this from time to time. It's even used as a reference architecture for like in a lot of different conferences and a lot of keynote speech. Okay, so essentially people are purchasing, when they're building this AI factory or their own data center, they also often put a high-speed in-cluster storage, typically some high-speed supercomputing storage, closer to the GPU clusters. I term this as a high-speed in-cluster storage. And employ certain data migration or data copy process to move data, to copy data from their centralized data lakes into this in-cluster storage before they can do training, before they can do inferencing. Okay. Well, this is pretty straightforward, right? You cannot rely on the GPUs talking to the data lake directly if they are not in the same region, especially these days, a lot of them are on-premise. But the problem is, so actually, a lot of people are following this practice. But the problem is, it requires extra steps. It creates just another or multiple different data silos. Okay? It requires preparation steps. For example, copy and validation before you do any GPU training. According to some our customers' observation, this can add a day-long process before someone wants to train that data set for 20 terabytes living in S3. They need to copy the data down to this high-speed storage. But more time is spent on the data validation part to make sure the data set is sound. And also, during this process, there might be cloud egress cost compared to just like doing the copy once, because different teams, they can be out of coordination, and they can do this out of coordination and multiple times. So this can also create large bills for the data set transfer repeatedly. Okay. And also there's, even in a way, like for example, you have multiple different GPU AI factories, but if one GPU factory is full, the GPU utilization is too high, it's very hard for you to right away use another GPU cluster. But one of the reasons you have to prepare the data again, right? So you have to make sure the data is mirrored across all the different places. Lastly, you have to operate in a way to maintain storage organized and under capacity, and requires extra coordination across different teams, different products. Of course, you can buy a lot of this storage to make it work. And then basically you are paying N copies of your data at a very expensive storage. So that is basically, I'm talking about like for the data lake, I'm talking about petabytes or tens of petabytes or even 100 petabytes scale. And for this storage, high-speed storage, I don't think you can pay, people typically don't want to do that, just to copy this data multiple different times. Okay, so what I'm trying to propose here, or this is basically reasoned based on my conversation, our company's vision, is that we want to build an AI data orchestration to unleash the data velocity. So instead of having another data silo, let's put a layer in between your GPU cluster, your GPU training or GPU inferencing workloads, and the data lakes. Because we believe the cloud storage is indeed the best choice for you if you have that scale of data, if you have that scale of, for example, availability requirement. And that is really the very good solution. So what you need is not creating another data silo and maintain the data silos on your own, but instead using a layer of AI data orchestration to help you to manage the data so you can freely access the data lake. Okay. So in my mind, the core capacities of this data orchestration layer should require first the data virtualization. So basically, it should provide a logical view of any storage or combined of any storage. So it decouples first the physical address, and second, the concrete API protocols, how you really want to reaching the data. So by having this layer, another layer of indirection, we have this semantics bridging, can simplify the application's view how to access data, and also have the location independence. Next one is high performance for data access. Okay, scalable data caching, data prefetching, optimize the data layouts, all this you can add them to help you locate and also to fetch data just like you're locating, you're reaching a data but in fact, it's perhaps backed by a remote cloud data lake. The third one is scalable data management. No one likes to manage data. So this layer should help you to intelligently, for example, manage the local storage on different GPU machines or possibly dedicated machines with NVMe's, or the existing fast storage, HPC storage you have already purchased. So this layer should help you to manage this disk resource, but present them as a logical layer to your applications. So you don't need to think about or even be aware of this implementation details. So this will enhance the efficient data storage utilization and automate the data placement. Okay, so I'm talking about like one of the implementation in my view is Alluxio. They started open source from UC Berkeley AMP lab in 2014. Okay, so one of the key feature we're implementing is this virtualization or unified namespace that basically it's mapping the data, giving the applications a logical file system, so you can mount different concrete storage system concurrently into this logical namespace. So you can think each Alluxio logical path can be mapped into a persistent storage physical address, and people can pick their logical address or original storage address to access the data. Another key feature this system providing, like for example, to help the speed to performance is really distributed caching. And we are having this consistent hashing way to organize the sharding or how to fetch data to optimize for performance. I won't go to the details, I'm just using this example. So during the past few years, we also developed, like for example, this is a lot of times these are proposed by the users that the advanced capabilities of this orchestration layer, so what it can do. One very interesting idea is to offload compute or part of the compute into this layer. Given this layer already has this hot data, so let's do some maybe a little bit predicate push down, even not the entire predicate push down, or some data transformation. In this way, you can reduce the network transfers and save the cost of a data serialization or delivery, and make the computation lower resource consuming on the application side. And cost optimization. So these days, the cost on the cloud storage is really based on how many APIs, not only just like volume you are transferring, but also how many APIs you are calling into these services. So if we can do some smart thing there, so we can reduce the cost too. Again, like I'm not going to the details, but like providing you some case studies. So this is one of the case study provided by Coupon, which is the leading retail company. And they're providing their views of how they can leverage a caching, distributed caching for their data lake to solve this GPU training problem. So yeah, they have multiple different GPUs in different regions and in the on-premise GPU clusters too. And they have this GPU, they want to really optimize for the GPU utilization and to guarantee the high I/O throughput, but also developer experience. So if you're interested, you can take a look at their blogs. So one of the architecture change they're trying to add is to this distributed caching layer between their GPU training clusters and these GPU data lakes. And just like as we proposed as one AI data orchestration layer. So by having this change, you can see the benefits from the model developer's perspective. One is the instant data availability, because with this layer, AI data orchestration layer added, so the source of truth is always the data lake. So you don't have to do the data migration, data preparation manually, but instead you can start the training jobs as long as you want to read the data. And second, it improves the GPU utilization across different regions. For example, it provides a consistent view of data passes from different GPU clusters. So if one GPU cluster is not having sufficient capacity, you can always submit the same job to a different cluster without waiting for the data to be prepared. But again, like I'm trying to emphasize, there's no black magic. Like we cannot just create the data in the vein. So for the first time you're accessing the data, we still need to access data at a speed of this you're reading from this cloud storage, right? But after that, the subsequent data access will be very fast, benefiting from the previous data access. Faster training jobs, so we have, like for example, we have some data showing that our customers seeing this kind of approach can see actually 30 to 40% faster job training, model training compared to high-speed storage solutions like AWS FSx. From the platform engineer's perspective, it helps also in a few different ways. Reduce the storage cost and operation overhead by avoiding the full capacity storage purchase and also eliminating the duplication. No egress cost on repeated data access and easy to expand. For example, this is very native to Kubernetes. You have this Kubernetes operator or Helm chart. You can simply just start operator to bring up this cluster, and yeah, it works. Like within a few minutes, you will have this cluster up and running in Kubernetes. Okay, so I want to talk about a second use case. This is also very interesting because, for example, in the first case study, we have seen if you have the data in a different data and GPU, they are in the different locations. But in this case, we're talking about even in the same region, you're inferencing workloads and your data is even in the same region. You may still want the actual low latency. I'm talking about sub-millisecond. I'm talking about like a sub-millisecond to get the data from this data lake. Yeah, so I'm going to talk about one of the joint work with it's an engineering collaboration with Salesforce, and show how we can use this AI data orchestration layer to help that, because they, like for example, they do have the problem that they need to serve many petabytes of the data underneath in the S3, but they want to achieve sub-millisecond latency when they have engines, for example, the agentic engines, to query the data into petabytes of data set and returns within sub-millisecond. When we are fixing this, any questions so far? Happy to take questions. Okay, cool, thank you. Okay, so for example, if you have the agentic applications, one way to really guarantee you have a very fast data access is through some in-memory solutions like Memcache or Redis, right? But the problem is, if you're talking about, like these days, we're talking about if you want to support a long-term memory for petabytes or larger, it's not scalable or it's too expensive. So the way, this is a different challenges here. You have the massive scale, you want to query this really large data lake, and you have the high storage costs of in-memory solutions can be typically limited or too expensive to serve all the requests. And also high operational costs if you want to have the direct access to S3 that will have the network bottleneck or incur high cross-AZ costs. So by working with the Salesforce, we found a very interesting way to solve this problem by actually having two techniques. One is having the data, small subset of data, cached, but still respect the data lake, but having your data, the hot data, to be cached closer to the agentic applications. But also, you can have this part of a query offloaded into this, for example, into this data set, into this service. So in this way, you get a fast time to insight. I will talk about later, like why you can do this. The better CPU, and actually this is GPU or CPU computation efficiency, and lower storage costs because you don't have to use the in-memory storage solutions to store petabytes of data. Like the AI data orchestration layer should be able to use the local NVMe's or set up local NVMe's to have this storage capacity and reduce the egress cost and network cost. Okay, so particularly one of the interesting things we want to do is we want to, like, for example, if we just have a very simple AI data orchestration with like just employing the simple caching here, you definitely can improve the performance, improve the latency by a few X. But still, a lot of times it spends on really retrieving the data, multiple round trips, and also serialization and deserialization for the data you fetched. Okay, so what we're exploring is to adding a query offload, some kind of like a query, a little bit of small query engine you can think, put it inside for this data orchestration layer. And then, used to be the case, you have to multiple RPCs to get the data, but now you just put a single RPC, and we will do a little bit more computation inside this data orchestration layer before return the results. It saves the round trips, and also by caching the important metadata, it avoids do the serialization, deserialization work. So on the right-hand side, we have some experimental results to show we're able to achieve really like 0.3 millisecond by having all this optimization together, compared to the naive approach, which you're querying on S3 directly. It takes 400 milliseconds. Okay. So if you're interested, actually we have a white paper, a tech report. It's a joint engineering collaboration with the Salesforce team. You can take a look of this white paper. Okay. This goes to the end of my talk. So summary, the data last mile problem is a critical bottleneck for the AI factories, we believe, which hinders the token velocity. The AI data orchestration, for example, can be one implementation by Alluxio, bridges the gap, providing data virtualization, the high performance access, and intelligent data management and computation offloading. We can optimize for data locality and GPU utilizations in the Kubernetes environment, and by accelerating the training and inference while reducing the cost. So key capacities like unified namespace, distributed caching, and compute offloading are essential, I believe, for the modern AI data infrastructure. Okay. So that is the end of my talk. We have 2 minutes left, so happy to take questions. No questions? Yeah. So don't put it too complicated. So essentially, thinking that way, if you have a Parquet file stored on S3, the simplest way you can write a Parquet reader application to talk to this data on S3, this Parquet file on S3. So the reader running on your EC2 machine may have multiple different round trips because Parquet file is really column structured. It has to go to the footer first and do some parsing, and then go to the write offset, pick the column group, row group, like this, right? So if you can, so that takes multiple different round trips. And also for the data you read, you also need to deserialize and serialize the data, deserialize the data, basically. So instead, if we can put part of the optimizations or part of the logic into this data orchestration layer, which is essentially a caching engine on top of S3, then with a single RPC, which is like giving this row key, give me the columns, these 3 columns, right? So that can be done in this layer to really reduce the round trips and improve the resource and also the computation latency. Yeah.
I see. Thanks for explaining. It's like a GraphQL equivalent idea, right?
Yeah, yeah. But this is really transparent to the application, but also transparent to S3. You still use S3 or data lake as a source of truth.
I see. Thanks. Thanks for explaining.
Okay, one more question. This is.
I was wondering, you mentioned that you were using Alluxio to deliver the data to the GPUs. And I was wondering if you use Alluxio from end to end, or you have some service in between in the AWS, except S3 and all that storage services.
Yeah, it's not end-to-end. It's really just a layer to, you can think it's access layer for your GPU applications or CPU applications. Okay, so your data is still on S3, on Azure, or GCS, and modified. We will not touch that, but we will read it. We can also, but your applications are accessing Alluxio rather than going to the GCS or S3 bucket directly. And we will help you to coordinate across different teams, right? If you have multiple different teams, they are all going to S3 or GCS on their own, they will be repeated or like insufficient or inefficient data access. Now we're making this coordinated.
Thank you.
Yeah, thank you. Okay, thank you so much. If you have more questions, I will be here around.